Welcome to Computer Architecture class. In this video, we are going to see about Unit 3 content, that is Design of ALU. Here, the first topic is De Morgan's theorem. Before going to see about De Morgan's theorem, first you know about what is Boolean algebra. It is nothing but a simple mathematics which involved only the binary numbers that are zeros and 1. It is also called logical algebra. This Boolean algebra is a fundamental concept that helps to design any electronic circuits. One of the Boolean algebra content is De Morgan's theorem. This Boolean algebra having some fundamental operations like and or not. In Boolean algebra, some important laws are there. First one is commutative law. If you are doing AND operation, irrespective of the order of these first and two elements, we can get the same result. That can be applicable also in OR operation. You can prove this law in this way. You can take A and B input, write the combination of these two numbers, then write the AND gate operation. Then you can swap the input. Then you can write the AND gate operation for B dot A. So these two values are same. So in this way you can prove this law. In the same way you can prove the second law. Next one is associative law. You can prove this law by writing first all the necessary inputs. In the left hand side, the first operation is B dot C. So you can find the AND operation between these two numbers and write the answer here. Then A and B dot C that can be involved in AND operation. The results can be written here. So this is LHS. In right hand side, first A dot B can be calculated. So that can be written here. Then A dot B dot C. These two values are involved in AND operation. So that can be written here. Now you compare these two values, you can get the same result. In the same way, you can prove the second rule of associative law. The third law is distributive law. You can prove the distributive law in this way. In the same way, you can prove the second law. Apart from these three laws, some more basic laws are there. First one is AND law. You keep the same value in the first input and you can change the values in the second input. You can get always these results. It means if any value in the first input, if the second input 0, the output is 0. If the second input 1, you can get the same value here. The same value in the second input, you can get the same input. If you get the complementary value for the first input, then you can get 0. In the same way, OR gate can be illustrated here. If the second input is 0, you can get the first input. If the second input is 1, you can get the value 1. If the second input is the same as the first input, you can get the same value. If the second input is the complementary of the first input, you can get the value 1. In this operation, if you involve the NOT gate operation twice, you can get the value A. You can check these values along with the truth table. Now let's move to the De Morgan's law. So it states that A dot B whole bar equal to A bar plus B bar. And also A plus B whole bar equal to A bar dot B bar. You can note one important thing. A bar can be also written as A dash. So A dash and A bar both are same. And A dot B whole bar can be written like this. This can be proved by using this truth table. So first we write all the combination of A and B values. Then in the next column, you can write the inverse value of A. In fourth column, write the inverse value of B. In your left hand side, A dot B whole star. In the first row, A dot B is 0. The inverse value is 1. In the second row, A dot B value is 0. The inverse value is 1. So in this way, you can write these values. In the right hand side, so you can write the OR gate result between these two columns. Now these two values are compared, both are same. In the same way, you can prove the De Morgan's second law. So this De Morgan's theorem and Boolean algebra that can be helpful for designing a electronic circuit, particularly in computer architecture. They are helpful to design adders, multipliers and some other circuits present in arithmetic and logic unit. Let's move to the next topic called adders. I categorize the different circuits in Unit 3 in this way. The first circuit is adder circuit, in which we are going to see about what is half adder, full adder and fast adder. For binary addition, first you take the two input and write the possible combination of these values. If you add these two values, you can get this result. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, the result is 10, 0 written here, and the carry is 1. So when you add these two binary numbers, you can get the sum as well as the carry value. In these three cases, there is no carry, that can be 0. So when you add these two numbers, you can get two different outputs. This is called off adder. Now we will going to see how this off adder circuit can be designed. For this designing a circuit, you should know about sum of product and product of sum. Using any one of these one, you can design a circuit. That means you can derive a logical expression that can be simplified by either Karnaugh map or Boolean algebra. For these two, we can choose sum of product because it is simple and mostly used for all designing circuits. So ignore this concept. So we are going to follow only sum of product for upcoming designing steps. First I am going to design this output. Here I write all the possible input values present in this truth table. They are multiplied first and the results are added and get the final result. So the individual products can be added. That is called sum of products. The next step is find the minterms. Minterm is nothing but selecting only the output one. We just ignore these two combinations. So these four components can be written like this. This is the first input, that is A. This is the second input, that is B. So that can be written like this. 0 means A dash, 0 means B dash. In this A is A dash, this is 1. So I can write the actual value. In this the first value 1. So I can write A. Second value is 0, that is B is 0. So I can write the inverse of 0, that is B dash. So I can write this value in this way. For these minterms, I can consider these two rows only. So I ignore the first and last value, only consider these two values. So sum equal to A dash dot B plus A dot B dash. So this is the expression for sum. The next step is to simplify this expression by means of either Karnaugh map or Boolean algebra. In our syllabus, we only deal with Boolean algebra. So you just ignore this K-map concept. So for this sum, this expression itself is a simple one because this A dash dot B plus A dot B dash can be same as the XOR gate. So instead of this, you can write the XOR expression. So sum equal to A XOR B. In the same way, carry can be designed by means of sum of products. So first I write all the combination value in a sum of product format. Then I find the minterm. This is the only one row having the output is 1. So I ignore first three combination. I can take only this value. So carry can be written like this. Here we no need to simplify this one. So sum and carry can be written like this. So I can connect first A and B into XOR gate, get the sum result. The same input value can be taken and subjected into AND operation and get the carry result. So in this way we can design the off adder. This off adder can be represented as logical diagram like this. If we add two binary numbers, this 1 plus 1 is 10, 0 is written here and the carry is written here. Here we can add three numbers, but half adder contained only two inputs. So this circuit is not sufficient for adding two binary numbers. It is only for single bit addition. But in real time, the binary numbers contains the combination of zeros and ones. These circuits only do the partial addition. That's why it is called off adder. So we need a complete adder circuit which contains three inputs and two outputs. That's why we are going to design full adder. The full adder can be designed by using two half adder connecting in this way. But in a procedural way, we should design a full adder by means of truth table. So we have three input. First write all the combination of three inputs from 0 to 7. So when you add these three values, you can get sum as 0 and carry as 0. So in this way you can fill the values for sum and carry. Now we are going to design this full adder circuit. For this sum, the minterms are these four rows. So I can write these four values as sum of products. The first value is 0, 0, 1, that is A dash, B dash and C. That can be written here. The second value is A dash, B, C dash. That can be written here. So in this way, all the values can be written. In the same way, the minterm for the carry can be identified. That can be written here. This is the design of full adder, but the design is not yet completed because when you are designing the circuit using this expression, it can take more number of logic gates. The next step is simplification. We can do the simplification here by means of Boolean algebra. First we take the sum expression. First I consider these two values. Here c dash is the common value. So I bring out this c dash. The remaining values are a dash b plus a b dash. So this is nothing but XOR gate. So I can write like this. For these two values, c is the common term. That can be written like this. This a dash b dash plus ab is nothing but XNOR gate. XNOR gate is nothing but inversion of the XOR gate. So I can write this expression in this format. Now I combine these two values here. And we already know the expression of XOR is nothing but in this way. In this expression, I can take this value as x and c as y. So it is x bar y plus x y bar. So we can write this expression in this component XOR with this c. So I can write like this. So finally, sum can be written in this way. In the same way, carry can be simplified by Boolean algebra. First compare the last two results. Here AB is common for these two terms. So I write like this. We already know the OR law. If the two inputs are complementary each other, the value is 1. So 1 multiplied with A dot B is the same value only. For these two numbers, C is the common term. So I can write like this. And A dash B plus AB dash is nothing but A XOR B. So this is the simplification of carry result. But we can do some more steps to reduce this expression. You just compare OR gate and XOR gate. Both the gate are same only the last row only differ. When you add two numbers, if the two numbers are 1, the sum is 0 and carry is 1. So the carry circuit cannot be followed when both the inputs are 1. So in this case, if both the values are 1, the carry value is. So for designing carry, A XOR B can be written as A or B. If we multiply this value, you can get C dot A plus C dot B plus A dot B. I can rearrange these values, we can get this result. So this is the two final expression for sum and carry in full adder. Now we can draw the logical circuits present in the expression. That can be logically represented in this way. So these three are input, these two are output. This carry can be also represented as Ci and Ci plus 1. That means if we add these three values, the carry can be generated. That carry can be input for the next full adder. Let's see two 4-bit binary number. First number is A, second number is B. Now you understand the meaning for this full adder. So the first number A having 4 bits that can be represented in A1, A2, A3, A4. In the same way, individual bit of B value can be written B1, B2, B3 and B4. That can be generally written as AI and BI. Initially, the carry is 0. If you add these three numbers, you can get the sum value 0 and carry is 1. So these three input can be added here. The sum 0 can be generated and 1 can be generated. For these 3 bits, we need another full adder and this one can be added with second bits of A and B. So this full adder can add these 3 values 1 plus 1, 0, it is the sum and it generates the carry. So this carry can be propagated into the third full adder. So these 3 values can be added by this full adder and the sum is 1, carry is 0. So these 3 numbers can be added by another full adder. So the sum is 0, carry is 1. So for adding two binary numbers, both are having 4 bits, we need 4 full adders that can be connected in this way. The generated carry can be taken by the second full adder. These 3 numbers are added, sum and carry can be generated. In this way, all the bits values are calculated. So the 4-bit full adder can be illustrated in this way. Suppose if you are adding two binary numbers having more number of bits, that means n bits. So we need n bit full adder. See this notation, instead of A and B, here X and Y can be used. This dotted lines denoted more number of full adders are there. Finally, if n value is 32 means this value becomes X32 and Y32. Now you just visualize how two binary numbers can be added by means of the combination of full adders. Here two 8 bits numbers are going to add. So we need 8 full adders. When we add these two numbers, first these bits can be added the sum and carry can be generated. During this operation, remaining full adders in the ideal state. Suppose if the full adder takes 10 nanoseconds for completing to generate the sum and carry, means after the 10th nanoseconds only, the second full adder is going to activate. So for this 8-bit, 80 nanoseconds needed to complete this operation. The reason is the carry can be propagated from one full adder into another full adder one by one. Finally, you can get the result. This carry propagation looks like a ripple can be formed in your water. That's why it's called n-bit ripple carry adder. So up to this, we are completing the full adder circuit. Now we are moving to fast adder. For this n-bit adder, the time delay can be happen due to the carry propagation. If the first full adder takes 10 nanoseconds, means this addition operation needs 80 nanoseconds to complete this process. If the two numbers are 64-bit number, means we need 640 nanoseconds to complete this addition operation. This is only because we are doing the serial addition operation one after another. If we have a circuit that can be added these two numbers parallelly and produce the addition result, means then the addition operation becomes fast. That circuit is called carry look ahead adder. In this example, I take 4-bit number. Here these two individual numbers can be added parallelly and finally updated with this carry look ahead logic. If we take these two numbers, these two individual bits can be added parallelly. So for each full adder, the sum can be generated as well as propagate and generate function can be generated that can be illustrated in this expression. Let's assume if a full adder can take 10 nanoseconds to complete this process. So this full adder can produce sum as well as P0 and G0. At the same time, the remaining full adders are also executed parallelly to produce the result. So in the first 10 nanoseconds, all these value can be generated. So we can get the sum value. Carry value can be calculated by this carry look ahead circuit and finally it can be produced. So it may take another 10 nanoseconds. So only the 20 nanoseconds we can produce the result. If the number of bits can be expanded, it cannot affect the speed of this execution because all the number of bits can be calculated parallelly and finally do this look ahead calculation and produce the final carry. Let's see how carry look ahead adder can be designed. It has two important functions are called propagate and generate functions. And sum and carry can be expressed in this expression. Sum equal to P XOR C, carry equal to G plus P dot C. First assign I value equal to 0 in this expression. So it becomes C1, it becomes G0 plus P0 dot C0. When you assign I equal to 1, it becomes C2, it becomes G1 plus P1 dot C1. In this previous expression, we already know what is the value for C1. We just assign this C1 value here. And after expansion, you can get this value. The next step is assign I equal to 2. Then it becomes C3. Then it becomes G2 plus P2 dot C2. So we already know what is the value for C2. So this value can be expressed here. So assign this value in this place, you can get these values. Then apply I equal to 3. Then it becomes C4. Then it becomes G3 plus P3 dot C3. So C3 value is there. You can assign this value here. Then you can get this expression. The important point in this expression is the carry 4 can be generated by means of the combination of G and P values and the carry 0. The C4 does not depend on C3 or C2 or C1. So this P0, G0, P1, G1, P2, G2, P3, G3, these value can be parallelly generated and we already know initially the C0 value. So from this value, it easily generates the C4 value. That is final carry value. In the same way, in C3 can be generated by means of combination of P and G as well as C0. This C3 does not depend on C2. Here there is no C2 and C1. Only C0 is there. So after generating these values and C0, C3 can be generated. In the same way, C2 and C1 can be generated. So in this circuit, there is no carry propagation. So the adder operation can be executed without delay. So this circuit is called fast adder circuit. In examination, you should derive this expression for designing this fast adder circuit. In part B questions, these three topics can be asked by designing either half adder, full adder or fast adder. Let's move to the next topic called subtractor circuit. We already know about the n-bit full ladder. This n-bit full ladder can be diagrammatically represented as in this way. Instead of a and b, it is denoted as x and y. I can take two values. This is x0, x1, x2, x3. The first input is directly connected to the adder circuit. The second input is connected through the XOR gate. The second connection can be connected with add sub control signal. This control signal can be connected to the control unit. First, understand the meaning for this circuit. In XOR gate, note the second input as 0. So you can take these two rows. If the second input is 0, the output is the first input. If the second input is 1, the output is the inverse of the first input. So it produces the ones complement number. So when add sub control becomes 0, this C0 value becomes 0 and all the second inputs are 0. That means your circuit produce the same value present in the Y that can be going into the adder circuit. So the X and Y value taken as it is and the results can be calculated. Suppose this control signals become 1, the C0 value becomes 1. So if the second input of the XOR gets 1 mean, it produces the inverse number of Y. So it produces the ones complement number here. Another one can be added in this way. So ones complement number plus 1, you can get 2's complement of Y. First number can be taken as it is. Second number is the 2's complement number means if you are adding these two, you can get the result for subtraction. So if you add these two numbers, you can get this value. You just recall the unit 1 concept for subtraction using 2's complement number. If the result has carry, you just ignore it. The result is the positive number. So ignore this carry. The result is 2. So in this way, this circuit can be used both adder as well as subtractor by means of this XOR gate design. So this is the subtractor circuit design. The next topic is multiplier. So in this topic we are going to study about circuit design of unsigned number, signed number and fast multiplication. Unsigned number is nothing but only positive number. We already know how to multiply these positive numbers. In signed binary number, it contains both positive as well as negative number. This negative number can be represented in any one of these three ways. First one is sign magnitude, second one is first complement, third one is 2's complement. Sign magnitude method is nothing but if you want to mention is positive 4, first you write the 4 value as it is and add one extra bit 0 for positive number and 1 for negative number. In first complement method, plus 4 can be represented in this way. You can include one more bit called sign bit. In negative number, you can invert all the values here including the sign bit. So minus 4 becomes like this. When you compare these two methods, this original value that is magnitude cannot be modified. Only sign value can be changed here. But in this case, this value can be totally changed into another form. In the same way, in 2's complement method, the minus 4 can be represented in this way. First we find the 1's complement number and then add with 1. Then you can get the 2's complement number. So when we are doing the signed binary number involving in multiplication, division or any other arithmetic operation, you should use any one of these three methods. In our syllabus, we only focus the 2's complement number. You just ignore these two methods because this is simple and mostly used for hardware circuit design. Suppose if you are multiply two signed number, the first number is plus 4, second number is plus 2. These two numbers may be in any combination. The first number is taken as multiplicand, second number is taken as multiplier. First I can write the 4 in 4-bit number. Then I add the sign bit as 0 because this is positive. Then I find the first complement number and added with 1 I can find the 2's complement number. So this is minus 4. In multiplier, 2 can be written as 1 0. In a multiplicand I can take 4-bit number, so I can add 2 0 here and added with one more bit for sign. For this circuit design, better you maintain the same number of bit for both multiplicand and multiplier and ensure that extra sign bit can be added. For this multiplication process, you need the negative number of any one of these two. So better you find the minus 4 value as well as minus 2 value. For example, suppose if your question asked 12 into 3 using sign multiplication, so first write the 12 value in 4-bit number. And 3 value is usually 2-bit number. I can add 2 0 here. Now I add the sign bit for this. And also find the 2's complement for these numbers. That means minus 12 and minus 3. Suppose the question can be asked minus 12 into 3 means you can take these two numbers. Suppose the question can be asked plus 12 into minus 3 means you can take these two numbers. Suppose both the numbers are minus means you can take these two numbers. So before going to the sign multiplication, you should know how to represent these negative values. Let's take some bigger number. If it is 25, 25 can be represented in 5-bit number. So I can make this 3 value as 5-bit number and add the sign bit and find the negative numbers. So after representing the multiplicand and multiplier value, then you can proceed the sign multiplication. So how to do this unsigned number multiplication, signed multiplication and fast multiplication, everything can be discussed in separate video in reading.com YouTube channel. The link can be provided in this description. Suppose the question can be asked in fast multiplication, the values are 147 into 23. Fast multiplication, you can use any of these three methods. In your question paper, these three methods can be explicitly specified. If not, you can use any one of these methods. Here I can use this first method. So this is absolutely signed multiplication. So before going to do the multiplication process, first I represent these two numbers properly. 147 is the multiplicand, 23 is a multiplier. 147 can be represented as 8-bit number. So I can make the 23 also as a 8-bit number. Then I add the 0 for positive 147 and positive 23. If I convert the negative numbers means the 2's complement of this number is minus 147. So this is the representation for this number. Now I am going to apply this concept. So the multiplier value can be recoded in this way using this table. Then this recoded value can be multiplied with the actual multiplicand that can be listed here. This process is already discussed in separate video. You can check the link. So without proper representation of this signed number, you cannot get the correct result. Let's move to the division circuit. These restore and non-restore division circuits can be explained separately in this video. In this division operation, we are going to do the subtraction process. So in this part also, you are using negative numbers. So the representation is very important. Let's take one example. Here 56 is the dividend, 7 is the divisor. First I can write the bigger value. It contains 6 bits. So I can make the 6 bits for the 7 also. Then I can add the sign bit. Then minus 7 can be written like this. So in this division operation, I need to subtract this 7. So in that case, this kind of representation is very important. So when you are answering this question, first you write clearly what is dividend and what is divisor, what is the representation of these numbers, and write the algorithm and draw the steps like this. Finally, you can tell which one is quotient, which one is remainder, and finally give the result as a sentence. The last topic is floating point number. You can refer this concept in this separate video. The Unit 3 title is Design of ALU. Design of important circuits like adder, subtractor, multiplier, division and floating point numbers. Don't forget to download the notes present in the description. If any query, make a comment. Thank you.